What does the crawling age of a 6-month-old baby have to do with the temperature outside?
Yeah, not an obvious connection.
Right. And why could drawing a seemingly logical, mathematically sound straight line through that data get you literally fired from your job? Welcome to the deep dive. We are taking you on a journey today through the exact mechanics of how we make sense of a really chaotic reality using math.
It's a fun one.
Our source material today is an excerpt from Chapter 8 of the Open Intro Statistics textbook, specifically looking at the science of linear regression.
Which, linear regression is one of those incredibly powerful statistical tools that you actually interact with every single day, even if you don't realize it.
Oh, totally.
Anytime you open a news article and you see a scatter plot, with the straight line drawn cleanly through this messy cloud of dots, you are looking at this exact concept in action.
Okay, let's unpack this, because our mission today is to demystify the mathematical engine operating behind those straight lines. We're going to figure out how we use statistics to find hidden patterns in messy data, how we leverage those patterns to make predictions about the real world, and most importantly, we are going to understand the strict limits of those predictions.
What's fascinating here is that we aren't just looking at abstract numbers floating on a chalkboard. We're looking at how these models connect to the physical world around you.
The messy real world.
Exactly. We'll be talking about everything from the exact cost of buying corporate stock to the specific biological measurements of a wild animal. I mean, it is mathematics applied to an unpredictable environment.
To set the baseline, we really need to talk about the myth of the perfect line versus the reality of nature. The textbook starts by showing us what a linear equation looks like in a completely flawless manufactured scenario.
Right.
They use the example of you logging into a brokerage account to purchase shares of Target Corporation stock.
Yeah, the stock purchase is it's a pristine illustration of a mathematical ideal. If you're buying shares, your total cost is perfectly linear. The textbook actually provides the equation for this transaction.
I have it right here.
Oh, go ahead.
The total cost is equal to 5 plus 64.96 times the number of shares.
Which makes intuitive sense when you break those numbers down into their real-world mechanisms, right?
Yeah, that 5 isn't just some random integer. It represents a flat $5 broker fee you pay just for making the trade.
Right, the cost of doing business.
Exactly. And the 64.96 is the precise price of a single share of Target stock. In this scenario, the number of shares you buy is what statisticians call the explanatory variable or the predictor variable. It explains what's going to happen.
And the total cost is the response variable. It responds to how many shares you buy.
Right.
And because this is a manufactured human system, there is zero guesswork involved. I mean, the textbook points out that the 5 and the 64.96 represent the model's parameters.
Right, the fixed rules.
Exactly. If you look at formal statistical notation, you'll see these represented by Greek letters. You have beta 0 for your y-intercept.
That's our $5 flat fee.
Yep. And beta 1 for your slope, which is the 64.96 per share price. So if you tell me you want to buy exactly 10 shares, I can calculate your total cost down to the very last penny.
But the text immediately drops a reality bomb on us right after establishing that pristine equation. It points out that perfect linear relationships are practically non-existent in any natural process.
Oh, yeah. Biological reality does not operate like a stock brokerage.
No, it really doesn't. In the real world, data rarely falls perfectly onto a straight line. Instead, when you map it out, it appears as this scattered, dispersed cloud of points.
To illustrate this shift from the perfect to the messy, the textbook introduces a study on the brush-tailed possums of Australia.
I love this example.
It's a great one. Researchers went into the field, they captured 104 wild possums, took specific body measurements, and released them.
And the core question these researchers were asking was whether they could predict the length of a possum's head based purely on its total body length.
Right.
And spoiler alert for anyone who has ever seen a wild animal, the data points do not form a perfectly straight line.
Not even close.
They form a loose diagonal cloud sloping upward. I mean, larger possums generally have larger heads, but there is immense variation. It makes me think of an analogy, actually.
Well, let's hear it.
That perfect stock market equation is like a very strict, highly regulated baking recipe. You put in the exact measurements of flour and sugar, and you get an exact predictable cake. But the natural world is more like a chaotic chef who always throws in a pinch of randomness just to keep things interesting.
I like that. And
Yeah.
that chaotic chef actually has a dedicated place in statistical formulas.
Oh, really?
Yeah, statisticians have a specific mathematical way to represent that pinch of randomness, and they use another Greek letter for it, epsilon.
Absolutely.
Right. Epsilon represents the error, the unexplainable variance. So your real-world model isn't just your starting point plus your trend, it's your starting point plus your trend plus epsilon.
So you literally have to mathematically acknowledge the chaos.
You have to. It's baked right into the equation.
Which brings us to the next massive piece of the puzzle. Since the possum data isn't a perfect line, how do we account for all those messy points hovering above and below the line we eventually do draw?
Right. How do we measure the mess?
Exactly. We move from drawing the trend to measuring our exact mistakes. This introduces the concept of the leftovers.
And the formal term for these leftovers is residuals. The foundational formula to remember here is beautifully straightforward. It's just data equals fit plus residual.
Data equals fit plus residual.
Exactly. Your actual observed data point is equal to whatever your model predicted.
Right.
That's the fit plus the leftover error, which is the residual.
Let's look at the specific equation the textbook calculated for fitting a line through that possum data. The equation is y hat equals 41 plus 0.59 times x.
And we should mention the hat.
Yeah, the text places a lot of emphasis on that hat symbol sitting on top of the way. That little hat signifies that the number we are calculating is just an estimate.
Right. It's an educated guess.
Exactly. It is an average expectation, not an absolute certainty like the stock market example.
And that distinction changes how we talk about the results entirely. Like, if you plug a possum with a total body length of 80 centimeters into that formula, the equation spits out a head length of 88.2 millimeters.
Okay, 88.2.
But you cannot go into the Australian bush, find an 80-centimeter possum, and guarantee its head will be exactly 88.2 millimeters.
Right, because of the chaotic chef.
Exactly. It simply means that, absent any other information, 88.2 is the average head length you should expect for a possum of that exact size.
To really understand the residual, we have to look at a real specific animal from the data set. The text singles out one particular possum that had a total body length of 77.0 centimeters. If we run that through our formula, so 41 plus 0.59 times 77, the model predicts this possum's head should be 86.4 millimeters long.
But the researchers actually took out their calipers and measured that specific possum's head. And the true observation, the physical reality of that animal, was 85.3 millimeters.
So the model guessed 86.4, but nature delivered 85.3.
Exactly. And the residual is simply the actual observed value minus the predicted value. So 85.3 minus 86.4 leaves us with a residual of negative 1.1 millimeters.
Okay, wait, I have to push back on this terminology for a second because it trips me up every single time I look at it.
What part?
If a model underestimates an observation, the leftover residual is a positive number. But if the model overestimates the observation, like it did here, the residual is negative.
Yeah, that's right.
That feels completely backward to how my brain processes the words over and under.
I know, it is a really common place to get tangled up. But if you think about the physical space on the graph, rather than just the words, it makes visual sense.
Okay, walk me through it visually.
Imagine you're looking at the scatter plot. If your real data point, the actual possum, is physically located above the prediction line, it means the real number was larger than your estimate.
Right.
So actual minus estimate gives you a positive number. The leftover physical distance is positive.
Oh, I see.
Yeah. And if the actual data point is hovering below the line, the actual number is smaller, so subtracting the larger predicted number naturally yields a negative result.
Okay. Visualizing the dots physically hovering above and below the line helps immensely. And speaking of visualizing, the text gives a phenomenal tip for evaluating these residuals. They describe creating what is called a residual plot.
Oh, the residual plot is arguably your most important diagnostic tool when doing this kind of math.
Really?
Absolutely. The textbook describes it as taking your original scatter plot and essentially tipping it over. You force the diagonal regression line to become completely flat and horizontal.
Like a flat horizon.
Exactly. That flat horizon line now represents zero error-perfect predictions. Then, you plot all your residuals as vertical distances above and below that flat horizon.
It essentially removes the distraction of the steep slope and makes it incredibly easy to spot any underlying hidden patterns in your mistakes.
Right. If your linear model is genuinely a good fit for the data, That residual plot should just look like random
The
noise.
chaotic chef.
Yes. It should look like a swarm of flies buzzing randomly above and below the horizon. But if you tip the graph over and you see a distinct curve or a funnel shape in your errors, it tells you immediately that your straight line is missing something fundamental about the true relationship.
Which brings up the mechanical question of how we arrive at that line. Like, how does a computer or software actually decide exactly where to draw the line through the scatter plot in the first place?
How does it minimize that swarm of residuals?
Right. To explore this, the textbook introduces a totally different dataset. This one looks at a random sample of 50 freshman students at Elmhurst College in Illinois.
Okay, shifting gears from possums to college students.
Yep. The variables we are comparing here are the student's family income versus the amount of gift aid they receive from the university. Gift aid is essentially free money scholarships and grants that do not need to be paid back.
And when you plot this out, the trend is visibly negative. As a family's income goes up, the amount of gift aid the university provides generally goes down.
Which makes sense.
It does. But it's incredibly messy. There is a massive amount of scatter. You have some high-income students receiving large merit scholarships and some lower-income students receiving less aid than you might expect.
It is a highly scattered cloud. So how do we find the absolute best-fitting line through that chaos? I mean, the intuitive approach would be to just measure all the physical distances of the residuals, ignoring whether they are positive or negative, add them all up, and simply draw the line that makes that total combined distance as small as possible. That sounds entirely logical to me.
It is logical. And the textbook even notes you could easily write a computer algorithm to do exactly that. It would actually produce a very reasonable, decent-looking line.
Okay.
But that is not what statisticians traditionally do. Instead, they rely on a method called least squares regression.
Least squares, meaning they're actively squaring the errors.
Exactly. They take every single residual, every mistake the line makes when guessing a student's gift aid, and they square it.
Wow.
You have residual 1 squared plus residual 2 squared plus residual 3 squared all the way through the data set. The software then calculates the specific line that minimizes that massive sum of squared residuals.
So what does this all mean for the actual data? Why introduce that extra layer of mathematical complication?
Well, the textbook lays out 3 specific reasons. First, it is simply the most historically established method, so there's an element of tradition.
Okay, tradition, sure.
Second, because it's the standard, computing the least squares line is universally supported in every piece of statistical software on the market.
Makes sense.
But the third reason is where the true mathematical philosophy comes in. Squaring the residuals disproportionately penalizes huge errors.
Let's ground that in the Elmhurst College example. It's almost like a grading system for a brutal exam.
As so.
Well, if your model misses a student's gift aid by $1,000, squaring that gives a penalty score of 1 million. But if your model misses another student's gift aid by $5,000, squaring it doesn't just multiply the penalty by 5. It results in a penalty score of 25 million.
Yes, that is exactly it.
Being off by 5,000 isn't just 5 times worse than being off by 1,000. In least squares regression, it is considered 25 times worse.
Right. It forces the line to try its absolute hardest to avoid those massive, embarrassing outliers. Let's say you have one student from a very wealthy family who somehow received an enormous, unusual scholarship.
Right, like an athletic scholarship or something.
Yeah, exactly. That data point is going to sit way far away from the rest of the pack. Least squares regression will actually pull the line slightly away from the main cluster of normal students just to get a little bit closer to that one extreme outlier, purely to avoid the massive squared penalty that would result from ignoring it.
So the line is risk-averse. It's terrified of being drastically wrong about any single point, even if it means being slightly less accurate for the majority.
That is a great way to put it, risk-averse.
Okay, so we have our risk-averse, least squares line locked in, but drawing the line is only half the battle. Now we need to grade its overall performance. We need a definitive score to tell us how strong this relationship actually is. That brings us to correlation.
Yes. Correlation is the summary statistic we use to quantify the exact strength of a linear relationship. It's denoted by the capital letter R, and it is strictly bound between -1 and +1.
+1 indicates a flawless positive trend. The possum data, but perfectly aligned. -1 is a flawless negative trend. The college aid data, perfectly aligned. And a correlation of 0 means there is absolutely no linear relationship whatsoever.
The data points just look like a shotgun blast on the graph.
Exactly. To show this metric in action, the textbook exercises highlight a fascinating real-world study conducted at the University of Denver. Researchers were observing 6-month-old babies.
Yes, the crawling babies.
They plotted the average age at which a baby first learns to crawl against the average outside temperature during the month that specific baby turns 6 months old.
And the correlation they calculated from this data was R equals negative 0.70.
Which is a surprisingly strong negative correlation for something as complex as human development.
It really is. It indicates that colder outside temperatures are strongly associated with a higher crawling age. Babies generally take longer to learn to crawl if they're hitting that 6-month developmental window during the dead of winter.
Right. And the physical reality behind this math, which the text implies, is that during colder months, parents bundle their infants in thick, restrictive winter clothing.
Oh yeah, like snowsuits.
Exactly. Those layers physically hinder the baby's movement and delay their ability to practice crawling compared to babies wearing light clothing in the summer heat.
It is incredible how a single R value of negative 0.70 can point you toward a physical reality, like winter clothing restricting muscle movement.
It really is. But there is a vital mathematical rule about correlation that the textbook makes sure to highlight here, and it has to do with how we measure our variables. In the exercises, they ask what would happen to that R value if the researchers had measured the outside temperature in Celsius instead of Fahrenheit, or, if they had measured the baby's age in weeks instead of months.
The R value would not change by a single decimal point.
Not at all.
Not at all. That is a fundamental, immovable property of correlation. The textbook reinforces this with another example involving body measurements, comparing height to shoulder girth. It notes that whether you measure the shoulder girth in centimeters or inches, the correlation remains entirely unaffected.
Okay, so changing the units of measurement might stretch out the numbers on the axis of your graph, but it does not alter the underlying strength of the relationship.
Exactly. The dots stay in the exact same relative position to one another. The math is completely blind to whether you prefer the metric system or the imperial system.
Which is a comforting thought, but we really need to transition into the most dangerous part of this entire methodology.
Yes, we do.
Here's where it gets really interesting. We have spent this entire time praising the linear model. We've talked about how elegant least squares is and how insightful an R value of negative 0.70 can be. But the textbook delivers a massive flashing warning sign about the blind spots of this tool.
What happens when nature stubbornly refuses to follow a straight path?
Exactly.
This is the most critical takeaway from the chapter. You have to remember what correlation actually measures. The R value only measures the strength of a linear relationship. It evaluates straight lines and nothing else.
And the text proves how dangerous this can be with a specific visualization in Figure 8.3. It uses data from a basic introductory physics experiment.
Right, the incline experiment.
The researchers mapped the angle of an incline against the total distance an object traveled when launched from it. When you plot this data on a scatter plot, the points do not form a line. They form the exact trajectory of a baseball flying through the air.
Like a parabola.
Exactly. It's a steep, symmetrical climb. It hits a peak, and it drops back down in a perfect arch.
And the relationship between the angle and the distance is absolute. I mean, it's dictated by the fundamental laws of physics. If you know the angle, you can perfectly predict the distance.
Yeah.
It is one of the strongest relationships you could possibly measure.
But imagine you're a data analyst who is rushing. You don't look at the scatter plot. You just dump that physics data into your statistical software and you ask it for the correlation. You ask it for the R value.
The software will dutifully do exactly what you asked.
Yeah.
It will use least squares regression to find the best fitting straight line.
Mm-hmm.
But because the data goes symmetrically up and then perfectly back down, the mathematical best fitting straight line cuts right through the middle and is completely perfectly flat.
This is the trap. The software is going to spit out an R value that is near zero.
Right.
If you rely solely on that summary statistic, you might confidently march into your boss's office and say, hey, I analyzed the physics data. R is zero. There is absolutely no relationship between the angle of incline and the distance traveled.
And you would be embarrassingly, fundamentally wrong.
So wrong. The variables are perfectly connected by a law of physics. The R value of zero simply means there is no straight line relationship.
The computer is entirely blind to context. It only knows how to execute the strict mathematical parameters you gave it. If the underlying reality of the data is curved or exponential or U-shaped, the linear correlation statistic will fail you spectacularly.
It will lie to you.
It will. This is why the textbook relentlessly emphasizes visualizing the data. You have to look at the scatter plot, you have to look at the residual plot before you ever trust a single number like correlation.
Wow. We have covered an immense amount of mathematical ground today. Let's take a breath and synthesize the journey you've just been on.
Let's do it.
We started with the absolute certainty of a stock market transaction, where an equation can predict a price down to the penny. We quickly abandoned that for the messy biological reality of brush-tailed possums, learning that we have to mathematically add epsilon, the chaos of nature, into our models.
We learned to measure our mistakes precisely using residuals, tipping our graphs onto their sides to expose hidden flaws.
We discovered that statisticians ruthlessly punish massive errors by squaring them in least squares regression, pulling our trend lines toward extreme outliers.
We learned to grade the strength of our models on a strict scale of -1 to 1, using correlation, unearthing why bundled-up babies crawl later in the winter.
And finally, we confronted the ultimate trap. A straight line cannot capture the arc of a baseball, and an R value of 0 does not mean reality isn't hiding a perfect curve.
It is a deeply powerful framework for understanding the world, provided you respect its limitations. And that leaves us with a critical question to consider, which the textbook actually teases as a preview for the next chapter.
Ah, nice. What's the preview?
Well, throughout this entire discussion, we've been predicting one variable based on just one other single variable. We guessed college gift aid purely from family income. We guessed a possum's head size purely from its total body length.
Right, simple one-to-one.
But human lives, financial markets, and wild ecosystems are infinitely more complex than a single input. What happens to our math when we start stacking multiple predictor variables together?
Oh, wow.
What if we want to predict that possum's head size using its body length and its gender and the specific geographic region of Australia it lives in? How much of the messy, unpredictable natural world can these models actually conquer before the equations break down and human intuition has to step back in?
Expecting perfect precision from the world is like expecting a chaotic chef to follow a strict recipe. But with tools like linear regression, at least we can begin to measure exactly how much chaos we are dealing with. Thank you for joining us on this deep dive. Keep questioning the numbers you see in the news. Always remember to look at the scatter plot, and we will catch you next time.